Okay. So now the fun begins. Right. We've got T and Z tests to deal with differences between, well, one group and a mean, or between two groups. That's, so far, we've talked about any sort of statistical test has been, at most, comparing two groups, right? Or one group to a population. Now, what if we had more than two groups? And of course, very often in any science, you have more than two groups. You might have a couple of controls and an experimental group. A lot of times with drug research, you have like a control group that's no drug, control group that is given a vehicle, right? So they're actually just given saline, and a control group that's handled and shown the big needle you're going to inject them with, and finally an experimental group against the drug. Very common to 3, 4, or 5 control groups in some of these studies. I once saw a talk at a conference, classical admission experiment that had 21 control groups. The guy took most of the time just explaining his control groups for his talk. They were all necessary. Like, oh, of course. It was amazing. So even if it's just one thing you're changing, you very often have more than two groups because you have a lot of controls. But maybe you have just different levels of all kinds of things. So here are some made-up numbers. And the independent variable is A and has 3 levels, 1, 2, and 3. So A1, A2, A3. So the numbers don't really matter here. But if we look at this, we have 3 groups of 3. And of course, the question we're asking here, are these 3 groups different? So with t-tests, we could do this. You could. You could do group 1 versus group 2, group 2 versus group 3, and group 1 versus group 3. You could. Well, do you see any possible problem with that? Sure.
It's time consuming.
It is time consuming. It's an interesting point. Most people wouldn't raise that, but yeah, you're right. It's just extra work. Other thoughts? Again.
Is comparing one group to another independently rather than all of them together?
Yeah, it might be that your hypothesis is not about is this group different from this one, this group different from this one, and these two groups different from each other. It's what's the pattern overall. So if that's your overall hypothesis is, what pattern am I expecting? Do I expect these to all be the same or not? You're actually not going to answer that question with 3 independent t-tests. The other problem is they're actually not independent. Right? So when you're comparing group 1 to group 3, group 2 to group 3, and group 1 to group 3, they all have a 0.05 level of significance. Suddenly now your significance level is inflated. Or sorry, your probability of the type 1 error is inflated. You could figure that out. You could divide 0.05 by 3, and then use that significance level, but that suddenly now we're losing statistical power. So there's a lot of reasons you wouldn't do that. Do just 3 comparisons. And no, 3 wouldn't be bad. But if you had a 4th group in, it's 1 versus 2, 2 versus 3, 3 versus 4, 1 versus 3, 4 versus 3, 2 versus 3. 1 versus 4. 7 comparisons. Oh, so this is not time consuming, and our alpha level is going to have to drop so much that we're not going to find significance. So in a case like anything more than 2 groups, you want something that's going to compare all the groups at once. If you can do that. And of course, obviously you can, or we'd stop the course here. So the question you got to ask yourself at the very beginning, we're going to sort of figure this out today from first principles. Okay? Instead of showing you a formula, you'll get that at the end. I'm going to talk about this from first principles. Why do the scores vary? The individual scores. Well, or in other words, what are the sources of variation? Well, individual differences is the first answer. So if we've got 9 different people, we're assuming those are all different people. They can be rats, I don't care what they are. But let's say people. Everybody's a little different. Even if there's no effect whatsoever of being in group 1, group 2, or group 3, everybody's a little bit different. And that's true of rats or people or anything else you guys. So it's individual differences. And that's always going to be there. If your variable has an effect or not, there's always going to be individual differences that are going to cause any variation. The other thing is there's going to be group differences, maybe. We designed this experiment. We hope there are group differences. We're trying to find out if they are actually there. So there's a possibility that being in group 1 or in group 2 or in group 3 is one of the sources of variation. There's really nothing else if you've designed the experiment properly. Right? So if you've been careful about experimental design, it should be the case that there are only, in an experiment like this, what's called a one-way or one-factor design, you should only have 2 possible sources of variation. Individual differences and group differences. Individual differences will always be there, group differences might be there, and we're going to see if we can find out if they actually are. Make sense so far? Okay. So, any score equals, well, some base level of just being a human that everybody's exactly the same on. And then, possibility of group differences. So everybody's going to have the same score for being human, which I believe is a sci-fi show. Plus any group differences, plus any individual differences. So there's no multiplicative factors in this. It's a completely additive model. Right? Does that make sense again? So all of that in here is there's a base level of being human, and then you go up or down depending on who you are, and you go up or down depending on what group you're in. Okay? So we can actually express that mathematically as x equals mu plus tau plus epsilon. Mu is the grand mean, where everybody starts. Tau is the treatment effect. And epsilon is error. And we use the term error in statistics, I've said this before, not to mean mistake. It's just stuff you can't. It's individual difference. It's not a mistake. So when I say error, I'm talking about stuff we don't directly measure, basically. Like we didn't put there. We put people into groups. We didn't assign people to their individual Hannah-ness or Dana-ness. So there's individual. So if we got this group here, here. I've assigned you to group 1, assigned you to group 2, assigned you to group 3. I've done that. You're all people, so there's that part at the beginning. And then the quote error is, being Sam or being Chris or being. There are different levels of being people. I didn't assign those because again, if I did, people would be lining up on Sundays to worship me, which I think is appropriate anyway.
Can you explain what tau is?
Tau just means treatment. Treatment. Group 1, group 2, group 3. What level of group are you in? 1, 2, 3. What level of person you are is the individual difference level. The fact that you're all people, you're all going to be the same on mu. You're going to be different on tau. You're going to be, your score is going to be elevated or depressed based on what group you're in. And that should be the same within each group. But different between each group. And the level of, in this case, person you are, or the error, the epsilon, is how much you differ based on just being you. Not being a person, but being your level of person. Okay? Makes sense so far? Mm-hmm. Questions? Yes, Dan?
Okay, so the individual differences, is that a level? Is that something that
there are
stays
levels.
there?
There's-
Same?
No, it's not level, it's different for every person.
So how would you possibly decide how different somebody is from somebody else?
Watch. You're about to find out.
Okay.
We actually don't care. Spoiler alert. We actually don't care, but we know that it's there. I know that you're different from Chris because you're Dana and you're Chris. For the same reason I know you're in group 1, and I know you're in group 2, and I know you're in group 3.
Oh, okay.
That's all. They're just different levels of a variable, and the variable here is we could give it numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, I can do that. Or I can use your names. I just think it's cuter to use your names. It's an odd way to put it. Cuter is quite the right word. It's fine, but it's not quite the right word. I don't know what word I'm searching for. I'll find one eventually. Other questions? Okay. So we call that the structural model of analysis of variance. Any score equals the grand mean plus the treatment effect plus error, individual differences. So there's some overall level that you all have. If I took, in fact, the average of all of your scores, I would do this here, 3 here, 3 here, 3 here. If I took whatever this experiment is, that's the grand mean. And then, because you're in group 1, your scores go up by 1 or 2 or 7 or 2.3, 8, 9, 11, I don't know, or E, or pi. Let's not use 2 notes. Let's not use mathematical. And yours go down, maybe, and yours go up, maybe. And then for individuals, for error, yours is different, 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 blah, 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 blah. That's 9. I added somebody else to the experiment. No, that's fine. No, I've added Bryce. Now we have an unbalanced design. Screwed everything up. Okay, so that's called the structural model of analysis of variance. This is going to be a thing that every single design we talk about, you're going to get this. You're going to be shown what's called the structural model. All this is doing is taking the stuff I've been saying and putting it into mathematical terms. It's shorter than writing any score equals being human plus a treatment effect plus individual differences. That's all that says. Nothing special about it. It just makes it a little easier to play with. All right. We have to make some assumptions. First of all, let's start out to assume that all groups are equal. We always assume that. It's called the null hypothesis. We assume the null is true. We start there and we try to prove it's false. So, mu1 equals mu2 equals mu3 equals ... equals mu k. Okay, there are k groups. In our case, 3. But in general, there are k groups. Okay? And because they're from the same population, that's what HO says, that means the variances are the same. Sigma squared sub 1 equals sigma squared sub 2 equals ... sigma squared sub k. All this is that HO is true. We always assume that when we do differential statistics. We start out by saying HO is true. Okay? Still with it? We're still good. Okay. That's our first assumption. It's simply the null hypothesis. We have always assumed this to be true. Now the assumptions get a little harder to understand. I'm just telling you that. Your scores on whatever this test is that you do are normally distributed, and they're random around the grand mean. It's also a pretty standard assumption. So if I was to take a look at all your scores and look at the distribution, I'm just saying they're all just normally distributed around the grand mean. The observations are independent. Okay? All that means is that Sean's score does not depend on Chris's score. If I know Sean's score, it doesn't tell me anything about Chris's score. Vice versa. And we can take care of that using design. That's the easy. This cannot be violated. The math falls apart if that isn't true. You can Yeah, you can violate that first one. You can violate it, okay. You don't violate the independence one, everything falls apart. Because it's about sampling and if you take over probability, we're talking about independent events versus dependent events, so to determine probabilities, it's going to become impossible. Okay, independent observations. And all sources of variation are in the model. So x equals mu plus alpha plus, sorry, that's getting ahead of myself. X equals mu plus tau plus epsilon. That's it. There's no other sources of variation. There's not because it's Thursday. Right? It's not even, there's not because there's lighting in the room. That's not there. Okay. If there were other sources of variation, where would they go? So let's say we did a shitty job designing our experiment. Where would, which of those terms would change? Sean?
Epsilon.
Yeah. Because I know I put you guys in groups, so I know that's a source of variation. I know you're different. And then there's something else that I had no control over. Oh, that's going to go into epsilon. So it actually there becomes error. So it adds on to the individual differences. It doesn't really add on to the individual differences. It adds on to the individual differences term in the model. You don't want that. Okay. All right. Now let's look at variance. And now it's getting mathy. We bring mathy in here. Sigma squared sub 1, that's the variance in the population for group 1, is roughly equal to s squared sub 1, the one we calculate, right? Because s squared is an unbiased estimator of sigma squared. Sigma squared sub 2 is roughly equal to s squared sub 2. Right? And these are variances within each group, aren't they? The variance within each group is only due to error. Because there's no variance, like if I look at you three guys, you're different from each other, not because you're in group 1, because you're all in group 1. It's just that you're different from each other, individual differences. Does that make sense?
Can you say the first part of that paragraph again? You said
No,
variance.
can I?
I think you can.
Okay. I appreciate the confidence.
Variance in a group is only due to
Into individual differences within each group. Because we're not comparing groups here. This is just within each group. Sigma squared sub 1, s squared sub 1. Sigma squared sub 2, s squared sub 2. I've treated you guys all the same. I've given you all level 1 of A of the independent variable. So any variance within this group is simply due to the fact that you're different people. Any variance within this group is simply due to the fact that not you're, because you all got A2, everybody got A2, level 2 of A. So any variance within this group is due to one thing only, and that's the fact that you're different people,
So
individual differences.
is that what analysis of variance is? It's always looking at how the individual differences affect your.
It's kind of like that.
Okay.
Yeah. Okay, go ahead. But that's where we're going.
Okay.
That's why I say here sigma squared sub epsilon. Oh, variance due to individual differences.
Oh.
Yeah, see, these little squiggles actually mean something. Roughly equals s squared, the overall variance of all the groups, of all the individuals within each group. And now this is where we're going to make a little bit of a leap. It's not a leap mathematically or logically, but this is where it's going to start to might get a little complicated. What I'm saying that if all the groups are equal, the average variance You're taking averages of variances? Yeah, sure. Numbers don't really come from. I got your variance, and your variance, and your variance. And I'm going to take the average of that. That should equal the variance, shouldn't it? If they're all the same. Yeah. What is J? There are K groups, and J is an indexing. It's the jth group. J equals 1, J equals 2, J equals 3. Okay?
Oh, okay.
Yeah, so it's just J and K. So J equals 1, J equals 2, J equals 3, eventually J equals K. In our case, 3 is K. So if I added up all the individual variances and divided by the number of groups, I should get this, which is roughly equal to individual difference variance. Okay. Questions? Yeah, don't feel bad about asking like, what's a J? I realize most of you haven't done math before. No, it's fine. We actually should require you to do 2 credits in math.
About the transfer.
Or there's talk of like a mathematical competency test. Nothing complicated. I think you should have one question. Here's the exchange rate. Here's how many liters are in a U.S. gallon. Does it make sense to go across the border to buy gas? Done. You can do that. You can mathematically competent. So questions about this. Does this make sense? You see how I got from this? So what I'm saying is basically this, variance due to individual differences in the population, is roughly equal to basically this. The average of the variances. So I get a variance here, I get a variance here, I get a variance here, I add them up, divide by 3. In this case, because K is 3. Okay. That's the first set. This is good. So I think you're all with me so far. Okay, it's getting a little more complicated. I'm building from simple to complicated. Remember the central limit theorem that I keep saying is really important and you should memorize? So the central limit theorem tells us that the variance of x bar, the variance of a bunch of means, should equal, does equal sigma squared divided by n. Right? That's just true. If you don't need a proof, it just is. It's a mathematical theorem. It's true. Okay? I am Pope Dave, and you believe everything I say. I'm infallible. So you're weird Catholics who believe in the Pope. I don't know what Catholicism is. As a baptized Catholic male, I believe technically I could be elected Pope.
That is accurate, yes.
Yes. I am also an atheist, so it would be interesting. Very strange.
I would like to see that.
Yeah, very strange. I would choose the papal. No, you could choose your name, right? Yeah. Well, yeah.
You get to choose your name.
Well, yeah. His name is.
Have kings.
What's the guy's name now? Who's the Pope now? Pope
Francis.
Francis. His name isn't Francis. It's
Yeah,
Guillermo something.
Guillermo Borgol.
Yeah. His name wasn't Frank. That's not Frank. So you choose a name. So I would choose Chad. or Todd. Just something. There's no way there's ever been one.
Chad, go with Chad.
And I would replace the tall hat with a jaunty beret or a ball cap. I think the chance of me winning is pretty slim.
Also probably.
Also true. Yeah. Yes. Run a series of negative campaign ads against other cardinals. Yeah. It'd be really weird. I am not making fun of anyone's religion. I make fun of all religions. I'm really not making fun of religion. But I think it's a nice way to think of this. It's just that I'm infallible if you don't believe this. It's just true. Or the central limit is infallible. Okay? So you get this? That's good. Oh, that means, we know that this is basically this. Variance of x bar is basically s squared of x bar. What's s squared of x bar? This is kind of a weird thing to think of. We'll take the mean of this group, and the mean of this group, and the mean of this group, and look at the variance of those means. We're getting a variance of means? The numbers don't know where they come from. You can take the variance of any set of numbers. So it's the variance of your means, of your mean, and your mean, and your mean. So we've got, I don't know, it's 8, 9, 10. Make it easy. And we're gonna just get the variance of 8, 9, and 10. Okay? You're still good. This is great. So that still equals that. Oh, why is it an epsilon? Well, it's variance, and the only variance we know is true because there's no difference between groups in our assumptions, is variance due to error, sigma squared sub epsilon. Okay? Yes,
What's the
Chris.
point of getting a variance of a bunch of means?
Well, think about this. Are the groups different? It's a really good question. If this group is, and this group, and this group, let's say they're not different at all, what should that number be? Which is the variance of the three means be?
Nothing.
Yeah. So it's a really
Tell
deep
us
question
if
you asked,
they're
actually. It's really cool. Pardon me?
Just to tell us if they're different? What's the point?
Yeah, the idea is to see if the three groups are different. Well, let's see if the three groups have different numbers. We know they're going to have different numbers. Let's see if the variance is here. The variance of these means is different. Because if I had three means and the variance was very small, I'd probably say, it's probably not very different. However, if the variance was big, I might look at that and go, oh, maybe there's something going on here. Make sense? It's a very good question. No one's literally ever asked that question. It's a really cool question. I want to estimate this, sigma squared sub epsilon, because we had that before. Remember that? I isolated sigma squared sub epsilon. Let's just do that again. How did I do that? Magic! No, I cross multiplied. It's just cross multiplied. Okay? So I just multiplied s squared sub x bar times n equals sigma squared sub epsilon times what was 1, because it's over 1. Now I've isolated sigma squared sub epsilon. It's funny, I've done two things, two separate calculations to estimate the same thing. They both estimate sigma squared sub epsilon. We have now two separate estimates of sigma squared sub epsilon. S squared sub x bar times n should equal the sum of the variances over k, and should equal sigma squared sub epsilon. Those two things on the left part there should be equal. That's called mean squared treatment. It's called mean squared error. One's mean squared treatment, one's mean squared error. Now let's take a look at this. We've started up by assuming that all the groups were equal. Let's pretend that's not true, because we're going to hope that's not true. Let's hope, in fact, that there's an actual statistically significant effect. You're different from you guys, from you guys. What happens here, mean squared error? What should happen? If the groups are different, should that change? Should the difference of that group, those groups are different, or if they're the same? Sorry, yeah, if the groups are different or the same. In other words, if the tau thing is non-zero. I've calculated, remember what that is? It's the average of your variance, and your variance, and your variance.
So if that's the average of the individual variance, then it shouldn't change.
It shouldn't change.
Yeah.
Even if your average is 26 and yours is 1,009 and yours is -4, it seems like there's an effect there. Well, radically different numbers. But because I'm calculating it within each group, these variances and averaging them, that shouldn't make a difference if we had this wildly different means, or your average was 6 and yours was 6 and yours was 6. Because I'm calculating it based on a group within each group. So mean squared error, or sometimes called mean squared within groups. You'll see either of those used almost interchangeably. There should be no, if there's an effect of the group being in a group or not, that shouldn't change that number. Because it's an average of variances within each group. This one will change. Because this is the variance of the means. If it's 6, 6, and 6, whatever. But if it's whatever those giantly different numbers were, or different, it's going to change. So this not only is an estimate of this, of sigma squared sub epsilon. So s squared sub x times n is not only a measure of sigma squared sub epsilon, it's also an estimate of variance due to being in different groups. So if the null hypothesis is not true, this value will be different from this value. So mean squared treatment will be different from mean squared error. Okay?
So the part on the left is like the variance between like different groups.
Yes.
And then the variance like on the right is within a group.
Exactly correct. So sometimes you'll see that called mean squared between groups and mean squared within groups, rather than mean squared treatment and mean squared error. They get used interchangeably. They mean the same thing. So if the null's true, these will be the same. If the null's not true, these will be different.
And so is it then, I'm trying to remember from the side class.
Yeah.
Is when you take like if they are different.
Yes.
Is there a certain point at which the difference starts to become significant, or is it
Yeah.
okay?
Yeah, because this is all, remember, these are all just samples. So we
Yeah.
can't, it's not from population.
Yeah.
So there's going to be some random chance difference that happens, right? I didn't assign you to these groups randomly. I actually assigned them based on where you sit.
Yeah.
It could be that that has some effect, I'm not sure. Of course, that would go into error variance, but still.
Yeah.
Even if I randomly assign you, random assignment, all that does is over a bazillion or an infinite number of trials make sure on average it's equal. It doesn't make on this instance that it's equal.
Yeah.
It's like when I flip a coin, and if I get 7 heads, I don't have a fixed coin necessarily, I might. But getting 7 heads doesn't mean I have a fixed coin.
Yeah.
You don't always get 5 heads if it's a fair coin. In fact, if you always get 5 heads, you'd likely get a fixed coin.
Yeah.
I don't know how you'd fix that coin, but you would have one, right? So it's got to be different by a big enough amount that we care.
So then, is this like the F values?
That's it's coming.
Okay.
It's
All
coming.
right. Yeah.
But think of this: when we calculate a t-test, we expect. Is there any chalk in here? Yeah. So if we had a t, we talked about this when I talked about power the other day. Just a bare bones vanilla t-test. Under the null hypothesis, the expected value of this, let's change that, the expected value of t given HO is true, is actually 0. But you hardly ever get 0 for a t value, even if it's not significant, because of just random fluctuation, because of sampling. Happily, the central limit theorem is like, sampling? Cool! That allows you to make estimates of variances. We never get 0. In fact, if you got 0, you'd probably go, that's weird. So the expected value of t, for example, is 0, but we hardly ever get 0. The expected value of how different these are would actually be, of how different they are, would be 0. But that's never going to happen. It's never going to happen. Well, exceedingly rarely it happen. Other questions? You're asking really good questions. Okay, is everybody okay so far? What you guys back here? Guys are good? Okay. I can't see that far. So I can't really go. I can smile. I saw a smile. It's hard for me to gauge expressions on people's faces when I'm not very close to them. And then it gets creepy if I just walk over here and start talking to you guys. Okay. I can read a room well, but sometimes it involves looking right at people. Okay. So if HO is true, the expected value of mean squared error is sigma squared sub epsilon. If HO, and if HO is true, the expected value of mean squared treatment is sigma squared sub epsilon. They should be equal. Yes? Those two values, if HO is actually true, in the real world that we really don't know about, we can't know because we have to know everything, and we don't know that. They should both be equal, and they should both equal sigma squared sub epsilon. Because if HO is true, those are both measuring the same thing, individual difference variance. Whoops. Oh, yeah, that's okay. If HO is not true, then the expected value of mean squared error is still the same. What happens, the expected value of mean squared treatment is actually sigma squared sub epsilon, sigma squared sub epsilon, I'm starting to talk like Christian Slater now, sigma squared sub epsilon plus n, number of subjects per group, times sigma squared sub tau. What is that? It's just variance due to being in different groups, which under the hypothesis is always 0. So the expected value of mean squared error should be less than the expected value of mean squared treatment, or is less than the expected value of mean squared treatment if HO is true. Or sorry, HO is not true. I'm confusing myself. So there's a lot of ways we think, well, how could we test this? How different is different? The first thing that always comes to mind when you think about this is, why don't we just subtract mean squared error from mean squared treatment? The problem with that is, what if the mean squared error is really, really small? And mean squared treatment, let's say mean squared treatment, let's make up some values. Can I leave the chalk here? I thought I did. I wrote something here and I did with the chalk. There's one piece of chalk here. Oh, there's two more here. Oh, great. Cutbacks. So, let's say mean squared error is 1. Let's make it trivially easy. And let's say that mean squared treatment is 1.1. And we would subtract mean squared error, mean squared treatment. We get 0.1. We look that up in some magical table. Okay. What if mean squared error is 0.00001, and then mean squared treatment is still equal to 0.1. The difference isn't that huge, absolute difference, but this is way bigger than this. So we're not going to just do subtraction. That would be insane. Right. What we're going to do is we're going to divide mean squared treatment. That's backwards. I should say mean squared treatment divided by mean squared error. Damn it. What this is going to give us is an estimate of proportionally how much extra variance mean squared treatment is measuring. So through variance, to go back to Chris's question from 20 minutes ago, by looking at variance or analyzing variance, mind blown, we are going to be able to find out if the groups are different. Are those different waters, Chris? Do you bring like different flavors, or no? You just bring lots of water. That's good.
Other shapes.
Other shapes. Oh, I see. Yeah, well, I don't see. That's why.
That's no.
Yeah, that's the issue. Chocolate.
Chocolate protein powder.
Delicious is delicious. I'm just kind of hungry. I don't want to eat because I don't. You don't want my mouth touching your. I mean, I get that, but I'm just saying. I'm hungry. I'll make my ramen in my office later. I just sit there. No one comes to my office hours, and I just sit there with chopsticks eating ramen. That's all I do. And then I watch Magnet. Like it's just You see my office lately, by the way? They're putting the new windows in. I'm now in a corner like this. It's horrible. Look.
Are we still putting the windows in? I say that and then I'm not actually sure.
No, windows are in, and now things seem to slowly happen. I seem to have window sills now.
Wow.
Yeah. One day Paul had a windowsill, and the next day he didn't. They took it out. So we're all very confused. What's going on with the windows? It'll probably get all completely done just in time for me to move offices. Just in time for us all to move over to CC. So it'll be like July. Well, your office is done, Dave. Also get out. So yeah, just sit there. So in other words, we're getting an estimate of tau. Now that's really a bit of I'm using that as a shorthand that I'm going to use all the time, but what I'm actually getting is an estimate of how much extra variance. It's not just this I'm getting, it's this. N times sigma squared sub tau, but it doesn't matter. I'm just going to always call that tau. So what's the expected value of, getting ahead of myself, am I? Yes. So this is precisely what we do in analysis of variance. It's amazing because when you think about it this way, this isn't exceedingly complex, is it? I mean, it's very clever, but it's not horribly difficult, I don't think, to understand. And it's one of those things that's like, oh, someone had to invent that at some point? Because it just seems obvious. Fisher was smart. Some of the best stuff, best science, to me, is stuff when you look at it and go, oh, come on, I could have thought of that, but I didn't. Right? It's like Darwin, evolution by natural selection. Everyone, when he came up with that, everyone went, of course, you bastard. Of course it's that. Why didn't I? Sort of like that with this, because it's really pretty simple, but it's also really clever. Fisher was smart. So the F stands for Fisher. F equals the F ratio, mean squared treatment divided by mean squared error. So mean squared treatment divided by mean squared error. What's the expected value of F if HO is true? Please.
1.
Yep. Because we got mean squared treatment over mean squared error. The expected values here are going to be tau plus epsilon over epsilon. And again, technically it's n times sigma squared sub tau plus sigma squared sub epsilon over sigma squared sub epsilon. But this, so don't show this to a math prof. They'd say, well, that's not technically true. And I'm going to say I'm not a mathematician. I'm not using this as a, I don't know what math prof I was doing an impersonation of there, but it wasn't anything here, I don't think. But that's just to understand it. It's shorthand. This isn't mathematically. But if HO is true, tau equals 0. So it's epsilon over epsilon. One thing divided by itself is 1. And 1 is the loneliest number. Somebody just for me. Songs from when I was very young. What's the expected value of F if HA is true? You said
Something else.
something else, but give me something more specific than something else. That is true. It's not 1, but it's something else. Please.
A value greater than 1.
Value greater than. Can it ever be less than?
You can mess up your data.
It mess up pretty bad, though. But it could be less than 1. Theoretically, it could be less than 1. They're variances. They can't be negative numbers. It's got to be greater.
You can't do that.
It can't be less than 1. Yeah, it should not be like 0.7 or 0.03 or something. If that happens, what does that mean? Sean was on to something. He said, messed up your data. But let's get get a little more specific. If you get something less than 1, what do you think happened?
Because the MST is the MSE plus the.
Yeah, tau plus epsilon.
Okay.
But so all the stuff we've said so far has led me to say we're taking tau plus epsilon divided by epsilon, and we have a bigger number divided by a smaller number, except we now get a number less than 1. We can't get a negative number.
Yeah.
If that happens, you've made a stupid mechanical error.
Yeah.
You've either entered a number wrong or you've reversed the 2.
You may have reversed the 2. Entering a number wrong would have to, no, that really shouldn't do it. That shouldn't do it. What would do it? Think back. Back 10 slides ago.
And they all put that.
I don't know if it's exactly 10, by the way.
The when you were saying the error, if there was, I can't remember.
All this stuff is true based on certain things.
Yeah.
Based
So
on,
the individual differences in the.
no, you're thinking too specific.
They're not independent.
It's a good guess, yeah. In fact, that's probably what happened. It's a violation of an assumption. All this math works because we assumed a bunch of things at the beginning. If we violate one of those assumptions, especially the independence assumption, though the homogeneity of variance assumption that's in there, sigma squared sub 1 equals sigma squared sub 2 equals sigma squared sub dot 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 equals sigma squared sub k, they have to be pretty much equal as well. So, does it happen when you analyze data that you get a value less than 1? It does happen, but as long as it's close to 1, you don't care. Because variation's going to be, and it's going to be like, oh, they aren't exactly completely, the variances aren't exactly equal, all that stuff, we're fine. When you get something that's like an order of magnitude less than 1, so like 0.01 or a couple orders of magnitude, you've really violated an assumption so badly that you're getting something that can't happen. And believe me, I see this all the time. I just reviewed an article for a journal the other day, and someone had an F value of 0.04. And I wrote in my thing, this can't be. This is impossible. The only way this is possible is if you violate an assumption. The assumption probably violated was homogeneity variance. I looked at your variances, one's 16 times bigger than another. You did not use the right statistical technique. Reanalyze your data. I'm Dave, and I'm Jerk. Go do more work. Actually, it shouldn't be that hard. Your data set's set up in XPSS, do it differently. And there are ways to fix it, which we will talk about next time, but there are ways to fix it. Okay. So it's always going to be greater than 1 if HA is true, 1 if HO is true. That's the expected value. That's theoretically. It's not real world, it's theoretically. Just like the expected value of a t-test under HO is actually 0. It doesn't happen. So if HO is true, then MST divided by MSE will be distributed as F with 2 sets of degrees of freedom. Treatment. Degrees of freedom for treatment, degrees of freedom for error. So, if not, it'll be distributed some other way. So basically, when we look it up in an F table, we say, well, how like it gives us, we get an F ratio, and we have the degrees of freedom, and then we look up the value, and it says, how likely is it that these come from the same, that these are actually the same, and if it's less than 0.05, we reject HO. Okay. So the top part of any variance equation is called the sums of squares because it's a sum of squares. It's a really easy term because it's a sum of squares. So sum of squares total equals sum of squares for treatment, sum of squares for error. What's the sum of squares? Well, sum of squares total is if I get the grand mean for our group of 9 here, and I just take your score, subtract the grand mean squared, plus your score, subtract the grand mean squared, plus your score, blah, 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 plus your score, subtract the grand mean squared. Sum of squares for treatments is your average minus the grand mean squared, then your average minus the grand mean squared, then your group's average minus the grand mean squared. Sum of squares for error is your score minus your group mean squared, plus your score minus your group mean squared, plus your score minus your group mean squared. Then we get to the next group. Your score minus your group mean squared, blah, 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 blah. Finally, plus your score minus your group mean squared. Those are sums of squares. And each of those has a number of degrees of freedom associated with them. There's a total number of degrees of freedom for all the data. Then there are degrees of freedom for treatment and degrees of freedom for error. Okay. Or we could do this more precisely, which is that. This is the sum. This is sum of scores total. The sum of each score minus the grand mean squared. This actually equals the sum of a group mean minus the grand mean squared, all summed together, times n, number of observations. I'm just going to weight it by number of subjects per group. Plus this, there's two summation signs. We're going to die. Sum of your score minus your group mean, your score minus your group mean, your score minus your group mean, plus your score minus your group mean, your score minus your group mean, your score minus your group mean, plus, and we do it for the final group. That's why there's two summation signs. And yes, technically those should have this up to this with the index on them, but I leave that out because it confuses most people. There are n minus 1 degrees of freedom. These are variance calculations. We have estimated to calculate this variance, this what's actually called mean square, but to calculate this variance, we have estimated one thing, the group mean. Or the grand mean, sorry. X bar sub g is grand. For the next one, well, there are k groups. We've estimated one thing, x bar sub g. You're saying, wait, Dave. What about that? We estimated those. No, the numbers don't know that. The numbers don't know that I calculated these means. So we have k minus 1 here. Number of groups minus 1. And over here, we have bn minus k. What? What's this? Well, think about this. Got stuff written on the board. Let's just erase that. So to do within each group, because we're going to get a mean for each group, individual scores minus their group mean. How many people do we have in each group? 3, but we call that more generally. And we lose a degree of freedom in each group. How many groups do we have? 3 or?
Okay.
Thank you. Oh, wait a second. K times n minus k. K times n. Wait a second, there's 3 groups. And there's 3 subjects. Oh, it's big N. So it's big N minus k. It's actually, if you want to get really technical, which you can, it's k times n minus 1. So I'm just simplifying it by calling it big N minus k. Big N is the total number of subjects per group in all groups. Little n is the number of subjects per group. Number of subjects per group times the number of groups is big N. It's the number of subjects in the whole experiment. So whenever this is called partitioning sums of squares. When we partition the sum of squares add up, and so the degrees of freedom add up to the total. So what we get when we're finished, when we actually do an analysis, and you'll see this in a sec, I'll show you how to do it in SPSS, it's dead easy, is we get sum of scores for between groups or for treatments, and it has k minus 1 degrees of freedom. And we lose a degree of freedom. And we get k minus 1 degrees of freedom. And we lose a degree of freedom. And we get k minus 1 degrees of freedom. And we lose a degree of freedom. And we get k minus 1 degrees of freedom. And we get k minus 1 degrees of freedom. And we get k minus 1 degrees of freedom. And we get k minus 1 degrees of freedom. And we get k minus 1 degrees of freedom. And we get k minus 1 degrees of freedom. And we get k minus 1 degrees of freedom. And we get k minus 1 degrees of freedom. And we get k minus 1 degrees of freedom. And we get k minus 1 degrees of freedom. And we get k minus 1 degrees of freedom. And we get k minus 1 degrees of freedom. And we get k minus 1 degrees of freedom. And we get k minus 1 degrees of freedom. And we get k minus 1 degrees of freedom. And we get k And the mean square is sum of squares for between groups divided by k minus 1. For within groups, it's big N minus k, sum of squares within groups, sum of squares of error, divided by n minus k. To get the f value, mean squared between group divided by mean squared within group. Mean squared treatment divided by mean squared error. They mean the same thing. We then get a value for f, whatever that value is, and we look it up in an f table to determine if the two groups, or three groups, or 11 groups, or well, let's just say k groups, are different from each other. So we say, okay, we got an obtained value of 7 for our f, and we got like, well, in our case, what do we have? We have k minus 1, so we get 2 and 7 degrees of freedom. So we look up the critical value for 2 and 7, with 2 and 7 degrees of freedom in an f table, and see if you exceed it. If you exceed it, at least 2 of the groups are different because HO is not true. So you just want to see if you exceed it. If you exceed it, you have different groups, or differences between at least 2 groups. You don't have, doesn't say which 2 groups are different, it says at least 2 groups are different.
2 are different?
At least 2 are different from each other.
Not just one is different from the other 2?
No, one is different from at least one other. At least 2 groups are different. Could be all 3 are different. Could be all K groups are different. But it might be that just group 1 and group 9 are different from each other.
But like group 1, group 2, group 3, group 4, group 5, 6, 7, group 8, all the same?
They could be. Yeah, because remember the null is just group 1 equals group 2 equals group 3 equals up to group K.
Okay.
The alternative is just, that's not true. So
Okay.
the most conservative way of saying that's not true is at least 2 groups are different. It doesn't tell us which 2 groups are different. There's a couple of ways to do that. One that we will talk about the next time, the next lecture. Well, yeah, it'll be the next day anyway. There's 2 topics next time. Or, so it'll be transformations and post hoc tests next time. Just to do that. Or you might just want to look at the data and see that, like, look, one group's way different from all the others. Do I have to do anything else? No. Right. Questions on this before we go into some SPSS and I stop recording?